Previously, we talked about determinants. Now we're going to talk about some properties of determinants. And there's some theorems that we're going to refer to. There's a theorem that says if A is an n by n matrix, that is a square matrix, then the determinant of k times A, where k is a constant, is equal to k to the n times the determinant of A, like this. And so let's actually test this on a 2 by 2 matrix. So let's say A is -1, 4, 2, 3, like this. I like to use small numbers when we know we're going to have to multiply things out so that things don't get too big. And so let's first find the determinant of A. Determinant of A, remember, is going to be upper left times lower right for 2 by 2 minus the upper right times the lower left. And it's going to be -3, -8, looks like -11. And then let's multiply A times some number. Let's multiply, let's say, A times 3. Let's multiply 3 times A. And again, remember, when we do that, we multiply each element by the 3. So we take 3 times -1. We get -3. 3 times 4 is 12. 3 times 2 is 6. 3 times 3 is 9, like that. So that's 3 times A. Now, according to this theorem, that the determinant of this matrix is going to be 3 to the n times the determinant of the original matrix A. Now, of course, in our case, we have a 2 by 2, so n is going to be equal to 2 because we have a 2 by 2 matrix. So first, let's actually calculate the determinant of this. The determinant of 3 times A. Again, that's going to be the determinant of what we have up here. And let me do the bars. Again, it's going to be the upper left times the lower right minus the upper right times the lower left. And let's see, the numbers are getting a little bit big. Looks like this is going to be 27. And what's that going to be? 72. And they're both going to be negative. So, and that looks like that's going to be a -99. So the determinant of 3 times A is 99. Now, according to our theorem up here, that should be equal to k to the n times the original determinant. So let's try that. So let's try again. Our K in this case is 3. And again, our N is 2 because it was a 2 by 2 matrix. So let's try 3 squared times the determinant of A. According to our theorem, that should be the same thing we would when we take the determinant of 3A. And so it's going to be 9 times the determinant of A was minus 11. And we minus 99, it checks. So that's an important thing to note, that if you're multiplying a matrix times a constant, the determinant is going to change depending upon the size of the constant and the size of the matrix. So it's always going to be the constant raised to the power, where the power is the dimension of the matrix, like this. And it'll always be the case that determinant constant times A is equal to the constant raised to that power N times the determinant of A. So it's a very important property. Here's a theorem closely related to the last theorem. This one says that suppose a matrix B is obtained by multiplying one row of a matrix A by a constant K, then the determinant of B will be equal to K times the determinant of A. So instead of multiplying the whole matrix by a constant, here we're multiplying just one row by the constant. And in that case, the determinant of the new matrix is going to be that constant times the determinant of the original matrix. Consider this matrix here. Consider this matrix again. Let me call it A. And A has 4, 2, minus 1, minus 6, 7, minus 3, 5, 8, minus 4. And if you were to calculate the determinant of this, you would find determinant of A is minus 11. You can check that yourself. And now let's multiply, let's say, one of these rows by, say, 3. Let me multiply this second row by 3. And again, we'll call that matrix B. And we'll multiply this row by 3. So that will be minus 18, 21, minus 9, 5, 8, minus 4. Like that. So now, according to the theorem up above here, the determinant of this matrix should be 3 times the determinant of A, because we took one row of A and multiplied by 3. And in fact, if you do calculate that, the determinant of B, and I'll let you go ahead and verify the determinant of this is going to be 3 times the determinant of A, which is going to be minus 33. Again, so note here we multiplied this second row. We multiplied the second row of A by 3. And of course, you can do that more than once. You could multiply, say, so here we multiplied the second row by 3. We could multiply the third row by 2, for example. And so let's say we go back to B here, multiply the third row let's multiply the third row by 2. And that gives us 10, 16, minus 8. Like this. So again, what we did, we multiplied A first. So we multiplied the second row of A by 3 and the third row of A by 2, like that, in order to get C. So therefore, the determinant of C is going to be determinant of A times 3, because we multiplied the second row by 3, but also we multiplied the third row by 2. So we're going to have to take the determinant of A times 3 and then times 2. And that's going to be the same as 6 times the determinant of A. So that would be 6 times minus 11. And it would be minus 66. Another theorem says that if A and B are n by n matrices, again, of course, that's implying, this statement is implying that the n is the same for both matrices. They're both either maybe 3 by 3, 4 by 4, 2 by 2, etc. Then the determinant of AB is equal to the determinant of A times the determinant of B. That's a really interesting property. It's kind of property that, if you look at the form that is, it's something that often does not come up with matrices, but for the determinant, it does. Now, one thing interesting, what does this imply? So remember, the determinant is just a number, and you can always commute real numbers. So if this is true, then that means that this is also equal to the determinant of A times the determinant of, the determinant of B times the determinant of A. In other words, what I'm saying is that if we carried this a step farther, we could say this is equal to the determinant of B times the determinant of A, like this. And simply because these are real numbers, you can commute them in multiplication. And now what does this imply? Because of this property up here, this implies that In other words, because the determinant of A times B is the determinant of A times the determinant of B going the other way, that means that this is going to be equal to the determinant of B times the determinant of A, like that. So what this string is telling us is the determinant of AB is equal to the determinant of BA. So we have several properties that come up here. The determinant of AB is equal to the determinant of A times the determinant of B. That's one property. And also we have the determinant of A times determinant of B is equal to determinant of B times determinant of A. Again, just simply because they're scalars, because they're real numbers. And finally, the determinant of AB is equal to determinant of BA. Again, this is really, in some ways, a surprising theorem because we know that in general, A times B for matrices is not equal to B times A. A times B is not equal to B times A, but if they're both the same size square matrices, then the determinant of A times B will be equal to the determinant of B times A. Very interesting property. Another important theorem says if an n by n matrix A is invertible, and what that means is, i.e., A has an inverse, then the determinant of A inverse is equal to 1 over the determinant of A, like this. And of course, you could also say this the other way, or if you just cross multiply, determinant of A is going to be 1 over the determinant of A inverse, like this. And so we can actually verify that by looking at an example we did in a previous video. Let's take a look at this example. Previously, we had a matrix A like this, and we found, again, this was in a previous video, that A inverse was given by this over here. Like this. And again, I purposely did not reduce these fractions because we're going to end up having to find common denominators, so we don't want to do that and then undo it. So let's actually test this theorem up above here. Again, this doesn't prove the theorem, but just a way to kind of see how it works. So again, the determinant of A is equal to upper left minus upper left times lower right minus upper right times lower left. That's 4 minus 10. That's going to be minus 6. Then the determinant of this over here, determinant of A inverse, upper left times lower right minus upper right times lower left. And the two negatives become positive. And multiply the bottom here, 36 minus upper, excuse me, multiply these together, 10, 36 like this. We get 6, excuse me, minus 6. Divided by 36, we get minus 1/6 like that. So we see that it's true that the determinant of A is equal to 1 over the determinant of A inverse, and vice versa. So for example, if you took determinant of A inverse, this is going to end up being minus 6. Or if you did it the other way, determinant, let's say if you had the determinant of A the determinant of A inverse, get that. So the determinants of A and A inverse are reciprocals of each other, basically. Again, it's a very important property that you'll use very often. Again, all these properties we've looked at in this video are true not just for 2x2 matrices, these are true for any square matrix. And so even though I'm demonstrating that they work for 2x2s, they actually work for any matrix. That is for any square matrix. Another important theorem involves the transpose. For any n by n matrix. A, any square matrix, the determinant of A is equal to the determinant of A transpose. Once again, let's just do a very quick example. So remember, let's say you have 3 minus 7, 6 minus 4. And remember the transpose, you interchange rows and columns. So the first column becomes the first row. Second column becomes the second row. And let's check the determinant. The determinant of A, upper left times lower right, minus upper right times lower left. So this is going to be what? Minus 12. And that 2 negative will be positive, so it's plus 42. So it looks like that's 30. And now let's look at the determinant of A transpose. upper left times lower right, upper right, times lower left. So minus 12, two negatives again, 42 is 30. Now on this one, you can say, wait a minute, it's looks like it's pretty obvious that it's going to happen for a 2 by 2. So let's maybe try it for a larger matrix and see if we still get the same thing. So let's go, let me call this B this time. I'm going to make the numbers not too big so I don't have to do a lot of calculations. 2 minus 2, 3 minus 1, 4, 1 minus 5, 2. And once again, remember the transpose is going to be this column becomes this row, this column becomes this row, this column becomes this row like this. So let's do the determinant. 1, 2, minus 2, 3, minus 1, 4, 1 minus 5, 2. Now, since it's a 3 by 3, we'll use that quick method. Again, if you're doing cross products or something, you don't want to do a quick method because things work out. They get more orderly if you use the regular method, but I'll use the quick method here. So remember, if you do the quick method, you rewrite the first two columns like this. Then you start with the first row and make an arrow down to the lower right arrow. Go along the first row like that. And these are all going to be the positive ones. And then start with the last row. Go up the diagonal like this. And these are all going to be negatives. So again, look at the first row, make an arrow in the diagonal direction. Those are all positive. Then go to the last row, make arrows in the diagonal directions. And then what we want to do is multiply all these numbers. So we take 1 times minus 1 times 2 plus, then go to this next one over here. 2, 4, 1. Then over here, minus 2, 3, minus 5. And then subtract these ones. Minus 1, minus 1, minus 2, minus 5, 4, 1, minus 2, 3, 2. And this is minus 2 plus 8. And this is 10. Those are going to be positive. That's 30. And then down here we have minus. That's going to end up being positive 2. And this will be negative of a negative 20. So it'll give us a positive 20. And this will be negative 12. So let's just be sure I'm doing this correctly. This is going to be 50. And minus 24. And we get 42. Now let's do the same thing for the transpose. Remember, what we want to do is copy the first two columns. 1, 2, minus 2, 3, minus 1, 4. Remember, we go along the first row, make the arrows down to the right. And those are all positive. And go to the last row in this direction. Those are all going to be negative. This is going to give us 1 times minus 1 times 2 plus 3 times minus 5 minus 2 plus 1 times 2 times 4. Again, I was just going down those diagonals. And then if we go up the diagonals, these are going to be negatives. -2, -1, 1, 4, minus 5, 1, 2, 2, 3, like this. And this will be -2. That's going to be 10, 30, plus 8, minus 2, plus 20, minus 12, like this. And actually, if we look at these numbers, they look very similar. We have a 2, we have an 8, and a 30. Those match. 2, 20, and so we should get 42 for this one as well. So the whole point here, again, this doesn't prove that it's true, but there is a proof available that it's true. This is just to demonstrate that it's true, that for any square matrix, the determinant of the matrix itself is equal to the determinant of the transpose that matrix. And there's another theorem that says if any two rows of a matrix are scalar multiples of each other, then the determinant of the matrix is 0. And now from our last theorem that the determinant of A is the same as the determinant of its transpose, you could say the same thing about scalar multiples of columns. And so you don't have to write this separate theorem. Let me just write it down. In the same way, if any two columns of a square matrix are scalar multiples of each other, then the determinant of that matrix is 0. And like I said, that comes directly from the previous theorem, because if you take the transpose of a matrix that has columns or scalar multiples, then that transpose is going to have those rows being scalar multiples. So therefore, the determinant is going to be 0. And so closely related to this, remember, the 0 row would be the scalar multiple of any other row. So you could write that as a separate theorem, even though this first one would imply these other two. So if any row of a square matrix is 0, the determinant of that matrix is 0. So right away, you can look at a matrix. And so, for example, let's say if you have, let me call it B this time, 1 minus 4, 2, 7, 17, 8, minus 2, 8, minus 4. So notice row 1, if you take row 1 times minus 2, will give you row 3. So row 1 and row 3 are scalar multiples. So the determinant of B has to be 0. Again, if you take negative 2 times this, you get negative 2. Negative 2 times this, you get 8. Negative 2 times this, you get negative 4. So row 3 and row 1 are scalar multiples, so the determinant is 0. Or let's say if you have a matrix, like I said, same thing works if columns are scalar multiples. So let's say if you have a matrix C and 5, 52, minus 10, minus 7, 6, 14. And so a row of this matrix is 0, is all zeros. So the determinant of this matrix is 0. And once again, I didn't write it up here. Same thing would be true if any of the columns had all zeros. The determinant of the matrix would be 0. And finally, let's take a look at this theorem. Suppose A is a matrix, probably should say an n by n matrix, a square matrix. And suppose B is obtained by interchanging any two rows of A, then the determinant of B will be negative the determinant of A. So if A is then by a matrix and B is obtained by interchanging any two rows of A, in other words, you keep everything else the same except you interchange two of the rows, then the determinant of the new matrix will be negative the determinant of the original matrix, or vice versa. They'll be the determinants will be negatives of each other. Let's go back to our previous example and just demonstrate it's true. Again, it doesn't prove it's true, just demonstrating. So let's say we had this matrix B here. We found the determinant was 42. So let's do this. So we had B before, now it's 1, 2, minus 2, 3, minus 1, 4, 1, minus 5, 2. And we determined that the determinant of B was 42. So now let's interchange two of these rows. So let's say let's call the new matrix C. Let me interchange let me interchange the first row and the last row. Like this. And let's find the determinant of C. Once again, it's a 3 by 3. We'll do it the quick way. So again, down this way, down this way, down this way. This way like this. And let's calculate these. 1 minus 1 minus 2 plus minus 5, 4, 1, 2, 3, 2. And then going up this way, 1 minus 1, 2, 2, 4, 1, minus 2, 3, minus 5, like this. Again, these ones were all positive, multiply these together, plus these together, same thing up here, except these are negative. So let's say we have this is going to be 2, negative 20. That's going to be what? 2 times 6 is 12. And this will be negative of a negative. That's going to give us a positive 2. And then this is going to be negative 8. And here we're going to have negative 15, another negative, another negative. Looks like it's going to be 3 negatives. So it'll be minus 30. So let's see what we're going to have here. This is going to be, let me put a couple of these together. Minus 18, 14, minus 38. And this is going to be minus 4 plus minus 38 is minus 42. And notice that's the negative of our original matrix. So again, we obtained C by interchanging 2 rows of B, and the determinant of our new matrix was the negative of the determinant of the original matrix. Now again, this property will work for any size matrix. Here I just did it for a 3 by 3. And of course, if you make 2 such changes, of course, you'll get to the determinant of the original matrix again, right? Because let's say if we had made another change, so let's say next we would maybe interchange row, say 2 and 3, then we would have taken the negative of this. So if you make 2 such changes, you'll have a negative and negative, and we would have gotten back to the original determinant. If you make 3 changes, it'll be back to negative again. So for every pair of changes, of every pair of interchange of rows, you will change the sign of the determinant. So if you do it once, it'll be negative the original. Do it twice, you'll be back to the original. Do it 3 times, it'll be the negative original, etc. Now again, the same thing works if you interchange columns. The same property applies. Again, that's because the fact that these kind of theorems, we know that the determinant of a matrix is equal to the determinant of its transpose, so that the things that work for the columns will work for the rows and vice versa. And previously, we had a theorem which says the product of the eigenvalues of a matrix equals the determinant of the matrix. So if you know the eigenvalues of a matrix, then you just multiply them together to find the determinant. And then we also had another theorem that said the eigenvalues of a triangular matrix or the diagonal elements of the matrix. So if we happen to have a triangular matrix, then we can just read the eigenvalues right off the diagonal. So for example, let's say you're given this matrix. Let me give it a different letter this time. Let's say call matrix G, and 3, 0, 0, 0, 14, 1, 0, 0, 8, 4, 5, 0, and minus 6, 18, minus 4, minus 2. So notice this is a lower triangular matrix, but it's a triangular matrix because on one side of the main diagonal, either above or below, we have the case that all the entries are 0. So this is a lower triangular matrix because the place where there are non-zeros is below the diagonal. So therefore, it's a lower triangular matrix. Like this. So the eigenvalues are 3, 1, 5, minus 2. And again, we know that the determinant then is going to be the product of the eigenvalues. So the determinant of G is 3 times 1 times 5 times minus 2. What is that? 15 looks like minus 30. So again, remember that if you happen to have a triangular matrix, you can find the eigenvalues real quickly, and then you can find the determinant real quickly.